of variables or vectors and constraints, you get different kinds of questions that might require very different ways of thinking about solutions. Obviously, the more flexible your constraints are on these things, the more powerful your system becomes, the more expressive it becomes, which means more problems can be modeled in that. But everything comes with a price. The more expressive you are, the harder it is to solve. Right? So there's always this tension between finding the level of abstraction for your problem that's just right, where you can solve it, but you're not doing it. And so one abstraction that seems to be a stable point here that's very powerful is linear programming, where you have continuous variables, linear objectives, and linear constraints. And we said that if you for such a problem, you can write it in this following manner, which looks like this. Any linear program can be written in the form maximize C transpose X, or some kind of linear function of the variables. You think of X as a vector, such that AX less than equal to B and X. Okay? The reason why this canonical form is acceptable is because if you have a min instead of a max, you just flip the sign. Same thing. It's linear, so you can do that. If you have greater than equal to constraints, you can flip the sign. If you have equality constraints, you throw both less than or greater than constraints. So this is without loss of generality, you can capture any kind of linear programming problem you might, any kind of problem with these kind of constraints you want to capture. Okay. So there are a couple of different things that we should explore starting from here. Linear programming, like I said, was not known to be in polynomial time until the middle 70s, till late 70s, when it was first shown to be polynomially solvable. And since then, there have been other methods to solve it in polynomial time. The polynomial time still depends on the actual. So if you think of these, there are different parameters here. So the parameters of a linear program are the numbers n. So typically we use n to refer to, so x, so I should put this here. So x is an n-dimensional vector. In other words, there are n variables in your system. So you have n variables. Now your matrix A is a matrix of basically one row per constraint and one column per variable. So you usually have n constraints, at least at the term we use for constraints. And then you have all the values. You have C, you have A, and you have B, which are constants. And there are many of them. So when you talk about linear programming being in polynomial time, it's polynomial time in the size of the input, which is this, which means n, m, and as always the log of the values of all these things. Right? Because for numbers, you think of the representation as log of their values. And in that sense, it's polynomial time. The question of whether you can design a linear program that's polynomial and depends only on these two things and nothing else is a big open. To this day, we don't know the answer. In other words, you might say, look, I don't want the running time of my algorithm to depend on the values. I want it to depend on the size, the real size of the problem, but not the values of the problem. It should be independent of that. It shouldn't matter what the actual values are of C, A, and B. Only the combinatorial complexity should matter. Whether we can design a solution that's polynomial in just n and m and doesn't depend on these, we do not know. We're close. Well, close. We can get something that's sub-exponential, but we can't get anything that's polynomial. I think the current bound is something like e to the square root of n. The best bound you can get for this is e to the square root. So I just want to point out that polynomial time means different things in different contexts. So in this case, it is polynomial time in the usual sense, but in a more strict, stronger sense of polynomial time, we're not quite there. Okay. But because you can solve linear programs easily, and because there are solvers out there, you can just download them and then run them. It's a very convenient kind of abstraction to have. And so there are two things I want to talk about today. First, very briefly, what happens if you change a linear program ever so slightly? So one change you can make to a linear program, which doesn't seem like a very big change, is to do this. And the 0, 1 at the end basically says each value is chosen discretely, like a choice. We saw these optimizations, we'll say it's 0 if it's this, it's 1 if you pick it, things like that, right? So it's a small change you can make. You go from a continuous variable to a discrete variable. Okay? And the 0, 1 could be 0, 1, 2, 3, 4. required. In fact, it doesn't matter that much once you get to 0, 1, because you can imagine if you have multiple values, you can write its bit representation that just expands. And then this linear program gets changed to something called an integer program. Okay? And the thing that happens when you do that is that you really change the complexity of the problem. And again, we haven't really talked about NP hardness. You may have heard about this before. Short answer is it's a intractable problem. Unlike linear programming, which is tractable, integer programming is not tractable. It's intractable. Okay? Just have one change. And this is one example I was telling you. You make small changes and things like this can happen. And as I mentioned last time, one of the cool things about flows is that you can write the problem of flow as an integer programming problem, and or as a linear programming problem. And fortunately for us, the solution turns out to be integral. So you get lucky. But in general, these two problems are quite different. Okay? And more often than not in algorithm design, you will take a problem. It'll be very easy to model it as an integer program. And then you'll say, well, that's hard. Let me just drop this constraint of being discrete and let it be continuous. You get the linear program. You solve that, and you somehow use that to find a solution to your original problem. Again, and that gets into the realm of what I call approximation algorithms. We'll be talking about that soon. But one way to understand why these two problems are different, right, is to realize that underneath, and this is true for a lot of optimization, or at least this is true the way I like to think about optimization, is that underneath all this algebra is hiding a lot of geometry. And if you were able to look at this and see it not algebraically, not using linear algebra, but using geometry, you will see interesting structure and insights into what this problem looks like in reality that will really help you. Okay? So what we're going to do today is we're going to talk about the geometric interpretation of linear programming. And this geometric interpretation can be applied not just to linear programming, to integer programming, to semi-definite programming, to context programming, to many, many kinds of programming. And you will find that, and this is especially true in machine learning, you will find that being able to move quickly between the linear algebraic view and the geometric view of a problem will turn to be very helpful for you to understand what's going on in a question. Or if you're reading a paper that is doing something and you don't know why it's doing it, it seems something weird, it might help us, if you write it out geometrically, this is what it's doing. So I tend to always take linear algebra, convert it to geometry. I used to have a PhD student who used to do the opposite. We used to fight all the time. But it was also very helpful because he could provide an insight that I didn't have, and I could provide an insight that he didn't have. And we wrote some papers together that exploited that fact, that you can go back and forth with these two insights. Okay? So that's what I'm going to do today, is talk about the geometry underlying linear programming, assuming that you understand this algebraic version of the problem. So maybe this is a good point to stop and say, does everyone understand, for both linear, integer and linear programming, what this means? Or why this captures an optimization? Remember, we argued this is just a linear function which you're optimizing, and each row of this can be thought of as a single constraint, so a linear constraint of the problem. And the matrix consists of the stacking up of all those different linear constraints. Okay? All right. So let's look at how to express this in geometry. To do that, we're going to, for a second, ignore the objective. We're going to ignore the thing we want to optimize for. We're only going to look at the constraints. What we're going to try to understand is, geometrically speaking, what are these constraints telling us? Okay? And to do that, we'll keep it sort of simple. We'll try to explain this in the language of, we'll do this in sort of low-dimensional space, so I can actually draw stuff. Okay. Imagine that my problem n has two variables in it. So let's say that n is equal to 2. So my variable is x1 and x2. Okay, someone give me a linear constraint involving x1 and x2. Anything you want.
O should be equal to 0.
Sorry?
Should be equal to 0.
What should be equal to 0?
Either of the variables should not be equal to 0.
Neither of them should be 0. Express it as a linear constraint. you said you want x1 not equal to 0.
Yeah.
How do you express that as a linear constraint? You can use less than equal to, you can use greater than equal to, you can use equal to.
So I can say x1 can be greater than 0 or less than 0.
I want one constraint. Give me one.
Okay, x1 can be greater than.
Okay, so we have a constraint, x1 greater than equal to 0. This is a relatively simple constraint. If we draw it out, right? If we call this the x1 axis and this is the x2 axis, what this is saying is that the x1 greater than 0 constraint looks something like this. Actually, let me do this. Something like this. This is the range of possible values for x. Okay. All right. Someone give me another constraint. Something a little bit more tricky.
x1 plus x2 should be greater than 1.
Okay. So let's write that down. Okay. Again, this is a valid constraint. Notice that if you wanted to write this in the form ax less than or equal to b, you could write this as minus 1 times x1 plus minus 1 times x2 is less than or equal to minus 1. Right? So just to point out that this is how you can transform these things conveniently. But we'll just, for now, since we know we can do that, we'll just go back to the easier one. So what does the constraint x1 plus x2 greater than or equal to 1 look like in the language of this plane here? So we can think of some values, right? So let's look at some edge cases. What would an edge case be? Well, x1 plus x2 is equal to 1, right? So one of those points would be somewhere here. Another point would be somewhere here. But you want it to be more than 1, so it's probably on that side. So it might look something like this. So if you think of x1 equal to 1 here, x2 equal to 1 here, and x1 equal to 1 here, there might be some kind of line here, right? And the constraint is going to be expressed as everything here, right? So in other words, if I was to stack up both constraints that have to be satisfied at the same time, right? What would the space of feasible values be? It would be something that looked maybe like this. Right? This will have infinity, and then you just sort of everything right? So as we're stacking up constraints, we're sort of obviously constraining our space in some way. And there's some interesting shape to this. And what have we seen? Well, in both cases, there is kind of something that corresponds to equality, which is the edge of that region. And then there's everything on one side of it, right? In the first case, it's this line and everything on one side of it. In the second case, it's this line and everything on one side of it. But this is, if we think about this, this makes perfect sense. Why? If we think of a general constraint, right? And we'll write it just for this case. A1, 1, x1 plus A1, 2, x2 is less than or equal to B1, which would be one row of that matrix operation, right? This is basically something, some constant plus some other constant less than or equal to some third constant, right? Yeah? If we replace this by an equality, the edge of this, right, looks like this. But this, of course, as we know, is the equation of a line in 2 dimensions, right? This is what a line looks like in 2 dimensions. Every line in 2 dimensions looks like this. And so what we're saying is that the edge of this region of feasibility is a line, and everything on one side of it, depending on the inequality, is what you want. This, by the way, is a geometric proof of when I said, oh, it doesn't matter if it's less than equal to or greater than equal to. Because if you have a line, what you're saying is either you take one side of the line or you take the other side of the line. It's still a line and something on one side of it. Right? It doesn't really matter. It's just which way you look at it. So now we can write a constraint, a linear constraint, is called a half space. We call these things a half space because it's half space. You take a line and you say it's on one side but not the other. Okay? And in this case, this is called a line. So you have a half space and you have a line bounding it. So every constraint looks like this. Okay? All right. If every constraint, so two things. So first of all, what does this look like in 3 dimensions? It's a bit hard to think about, right? So I can't really draw it for you, but let's go back to the linear algebra again, right? So in 3 dimensions, so in 3D, a constraint looks like, again, I'll just write it in simple things, a1x1 plus a2x2 plus a3x3, and we'll just use the equality equal to b. Right? What is this equation of? A plane, right? So if you have a piece of paper is my plane. Depending on the values of a1, a2, and a3, this plane will move. But it's a plane which goes to infinity, and the inequality says everything on. So it looks like this, everything this side. So in general, if you have a linear constraint, you can think of it geometrically as a half space. In 2 dimensions, a half space is a line and one thing on one side. In 3 dimensions, it's a plane, everything on one side. In 4 dimensions, you need something stronger to drink to think about it, but you can imagine this. These are generally called half spaces in arbitrary dimensions, and the object is not called a plane, it's called a hyperplane, like hyperspace, hyperplane. Okay, so I'll often say, look at the hyperplane in 2D, and you're like, what do you mean? That's a line. Yes, but just think of this as a generic term for any of those objects. Right? A space of codimension 1, if you want to be fancy. Okay. So now we know that each constraint that we're stacking up together is a half space, which is bounded by a hyperplane. And we're saying all of these things have to be true at the same time, right? Each of those constraints must be true. So you have to be on some side of this thing, you got to be on some side of this thing, you got to be on some side of that thing, and we're just adding them all up. And if you think of what that looks like, the plane, again going back to 2D, so intersect, so we're saying, what is the intersection of half spaces is basically ax less than equal to b. Because it's an intersection, because you're saying each of those constraints have to be such as an and. This is why when we talked about x not equal to 0, that gets a little tricky because that's an or. You're saying either x is more than 0 or less than 0. I'm not still quite sure we're going to encode this in our language. We may not be able to. That's a different story. So, what does this look like? Well, in 2 dimensions, we just did this. So let's draw 1. So this is okay, so let's see. So we'll draw. We'll draw this one. This is one line. I'm not actually going to infinity on both sides, right? And then there's everything on one side of it. This is my region of feasibility. But now comes along a new thing, maybe this way, and now its region of feasibility is everything on this side of it. right? Then along comes another one, and maybe its region of feasibility looks like all of this stuff. Right? And then along comes another one, and maybe its region of feasibility looks like everything here. If you take the intersection of all these things, what are you going to get? What you're going to get is a region that's bounded by this, 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 and this. It's a polygon. It looks like very modernist painting. So if you have this polygon here, so it worked out nicely that, oh, we can now say, okay, the collection of all these inequalities in the language of geometry, if you look at it, you should think of something like this. Now, will it always look like this? Can you think of a case where it may not look like this? Is there something about this that seems maybe a little bit too special, that's not fully general? That there could be things we can get from an intersection of spaces that don't look just like this?
Sometimes you might not get any feasible region.
You might not get any feasible. Let's see if we can create a situation like that. So how would that work? What's the simplest way you could imagine not creating a feasible region? In geometry.
Just all the lines are parallel.
If lines are parallel, that's not enough. You need one more thing.
The constraint is one should be greater than the other.
Okay, good. So let's say we have two constraints. This one has everything on this side, right? And we have another parallel line, as you pointed out, very parallel, and everything is on the other side. There is no feasible one. And a simple way to think about this is to say, we want to satisfy the constraints, I don't know, x plus y less than equal to minus 3, and x plus y greater than equal to 2. We know that these two constraints will give you two parallel lines, and there's, just by looking at the algebra, there's no way you can satisfy both these things at the same time. There's nothing stopping our specification of constraints from having stuff like this. But then we'll have no feasible answer. In other words, the intersection will be empty. That can happen, for sure. What else could happen? Another thing that could happen. So let me just write this down while you're going to say something, Pega?
So I don't know if it matters if the intersection part is convex or not.
I haven't really talked about convexity in this class. Could you explain what you mean by that?
So if we get 2 points in the region, the line which connects them exactly falls into the region.
Okay, so convex region is a region where any 2 points in the region, if you draw the line connecting those 2 points, it also stays in the region. So this is convex, because if I take any 2 points here, okay, there's something in this room that's very obviously not convex, of the same kind as this. Look at this table here. This is not convex. If I take a point here and a point here, the straight line connecting them does not go through the region, it goes outside. So things that have little bumps in them are non-convex. Things that are kind of more roundish-ish, not really round, but kind of always going around, are convex. So continue your question. Are you worried about whether the resulting region will be convex? So that's a good question. So now this is a little bit further afield, but we know you can prove that the intersection of 2 convex regions is convex.
Yes, but what is the difference of that?
Okay, this feasible region is the intersection of half planes. Every half plane is convex. Therefore, the intersection of all half planes is also convex. Therefore, what you get is convex. That's my proof. When you said difference, we're not doing differences here. We're doing intersections. So yes, the region. But what else? There's another thing that could happen that's not captured by this nice picture over here. We've captured emptiness. That's definitely a possibility. What else could happen?
Infinite number of solutions.
Infinite number of solutions. Doesn't this have an infinite number of solutions?
Yeah, this one has a bounded, right? Like
Okay,
also
so don't say infinite, say something else.
Unbounded.
The region could be unbounded. How could that happen?
Like if you take the red line out of from the the first diagram,
Yeah.
and another line, another blue line out of the diagram, then it would be a problem. So like you just
Yeah, take the red, the way I drew it, it's probably not going to work because eventually those things are converging.
Yeah, so just take two intersecting lines, that's it.
Okay, so for example, let's consider a very simple case when you have constraints x1 greater than equal to 0, x2 greater than equal to 0. Right? What does this constraint describe? It's a really simple one, and this describes everything. Here. It's kind of, if you think of it like a wedge, it's kind of going out in. So the intersection of half spaces could be empty, it could be unbounded, it could be bounded. You will say something?
And you have like one solution.
You could have just one exact solution, right? So for example, suppose you had a case when, what could be a case with exactly one solution?
So in this example, x was not equal to 0 and x was not equal to 0, adding to these.
X1 not equal to 0 is not constrained.
Oh, sorry, less than equal to 0 and x2 less than equal to.
As we said, we can have equality constraints, right? If I have an equality constraint, if I add now, as you were saying, suppose I add now x1 less than equal to 0 and x2 less than equal to 0, the solution of all of these is x1 comma x2 is equal to 0 comma 0 is the only feasible solution. You have 1 point. But one thing is always true about this, that the intersection of half spaces is a region that has a polygonal boundary, or what's called a polyhedral boundary. All its boundaries are straight. You have no curves. And again, this falls on the fact that each of these constraints is straight, so all the boundaries are going to be straight. So in fact, you can say, generally speaking, that and there's a proof of this in general in high dimensions, that the intersection of half spaces consists of a polygon plus a cone. So you may have both, right? So you either have the infinite part, which is your cone, or you have just a bounded part here. But for now, if you should, at some point you will be sufficiently experienced with this, so you can look at AX less equal to B and say, oh, that's a polygon. Or more generally, it's a polytope. Is what the general term for this is called. In 3 dimensions, what does it look like? It looks like some kind of, I used to bring these shapes, and I should bring it. You have basically like a polyhedral, like a multi-sided die or something like that. Like a 6-sided die, you can imagine a set of constraints in 3 dimensions. Everything inside it has a constraint. Okay? So this is what our goal is, right? Try to translate linear algebra into geometry by saying that AX less than equal to B corresponds to a polyhedral structure. And again, in 2D, it's a polygon, which could be open. Yeah?
Number of sides should be equal to the number of pieces.
Sorry?
The number of sides would be equal to the number of linear sections.
The number, so the question is, okay, it's a polygon of some kind. How many sides does it have? How big is this? What do you think?
I think it should be less than equal to
So the number of sides should be less than or equal to the number of constraints. In what dimension?
Oh, but yes, dimension. 2 dimension I can say this, but 3 dimension.
Can you say it in 2 dimensions? How would you do this in 2 dimensions?
If the two lines exactly like
What do you mean?
two constraints are on the same line.
Well, let me ask you this. Yes, can a constraint, so we agree that the whatever region we have is bounded, every piece of it is some constraint. Can that show up twice? You're saying yes, it can show up twice? Or are you nodding that yes, this is a good question? I'm not sure which. We'll pretend he said yes, it's a good question. Yeah. Okay. So yes, how many times can that line show up? In the intersection?
You can have different lines right together.
No, the same line. So give colors to all my different constraints. So I have the red constraint. In the final solution, how many different distinct pieces of red that are disjoint from each other can I have? So in 2 dimensions, with a bit of thought, you can conclude that it will only occur once. You can't have it occur more than once. And therefore, the number of pieces you can have is at most m, the number of constraints. In 3D, it's not that simple. In 3D, as it turns out, the number of the complexity of the polygon, of the polyhedron, you have to count both faces, you have to count edges, you have to count vertices. The total sum of that complexity you can still show is linear in the number of vertices and number of constraints. Once you get to 4D, this is not true. In fact, there's a theorem that says that the complexity of a polyhedron with m constraints in n dimensions, because there are n variables, can be I'm trying to figure out whether it's floor or ceiling. Oh, it's a floor. It can actually be exponential. The object that is used to construct this is very clever. It's a little tricky, but it's very clever. You can look at that. So in general, it's quite bad. It's exponential in the dimension. But in 2 and the reason why in 2 and 3 dimensions it behaves the same is because of the floor function there. So for 2 and 3, that exponent is 1. For 4 and 5, it's 2, and then it goes up with pairs. Okay? But it's a good question because that constraint space, the boundary of it, kind of gives a sense of how complicated this region is. So it's a good question to ask, okay, how difficult is it to describe this region? It turns out it's pretty hard to describe it. So I wouldn't want to write down all the different lines of it. I would want to keep it as, oh, it's the intersection of half spaces. Because if I do it this way, it's going to be very expensive. Okay, so we have successfully given a geometric characterization of the region of feasibility. What about the objective? What is the equivalent geometry that describes the objective function? So let's write down the objective function again. So we're trying to maximize. So let's look at the objective. We want to maximize C transpose X, right? Forget the feasible region for now. So we do something and we get, so we get C transpose X is equal to 1. And we're happy. Then we work a bit harder and we get C transpose X equal to 2. And we work some more and we get C transpose X equal to 3. Okay? And now we can say, okay, well, there's a whole bunch of possible values for X that would get me C transpose X equal to 1. And they're all kind of okay. They're not obviously optimal. And there's a whole bunch of different answers that give me C transpose X equal to 2. And they're also kind of okay. They're not optimal. But I worked really hard and I got C transpose X equal to 3 and I feel like, okay, that's optimal. But if you look at all the solutions for this equation, what does this describe? The equation C transpose X equal to 1, I can write as, again in 2 dimensions, I can write as C1x1 plus C2x2 is equal to 1. What does this describe? Well, in 2 dimensions. It's a line. It's a surface in 3D. There's a line in 2D. Sorry? Speak up.
You can consider as Z equal to C1 x1 and C2 x2. That is the equation.
No, but this is the equation of a line, right? In 2 dimensions. Ax plus by equal to C.
But then you have different values.
No, forget that. Just look at this one. Don't look at it. Just look at this.
That's a line.
There's a line, right? There's also a line. There's also a line. What do these lines have in common? Huh? They're parallel. Why? Because the coefficient is the same. So if I had to draw these lines, it might look like this, right? So depending on the values of C1 and C2, it might go this one way or the other. So this might be, you know, C transpose X equal to 1. This might be, oops, not too parallel, but you get the idea, equal to 2. And this might be C transpose X equal to 3. They're all parallel to each other, right? So if you want to think about optimizing this function, you can think of taking a line, kind of sliding it parallel. Right? And the direction you're going to slide it in is what? The direction you're going to slide it in is a direction that's perpendicular to the lines. And what do we know about that? That's the vector C1, C2. The vector C. So you can think of the vector C as telling you, which way you want to optimize, which now gives us the proof that max and min are the same. Why? Because maximizing is just going this way, minimizing is just going the other way. Geometrically, they're the same thing. Just in algebra, they look different. Okay? So we've got this. So this is, sort of a simple observation that the goal of optimizing a linear objective corresponds to essentially visually taking a line and sliding till it stops somewhere. Well, where would it stop? It could keep going forever. But it can't. Why? Because we have constraints. So now let's put all this together. So what is linear programming telling us? Well, it told us that the feasible region is some kind of polygonal region. We don't know what it looks like, and we know it can be unbounded. Now let's pretend it's not unbounded. Let's pretend it's sort of a closed region. So maybe it looks something like this. I don't know what it looks like, but it looks like this. Right? This is some description of what AX less than equal to B looks like. Every point inside this is a feasible answer. But we want the optimal answer. And so we have some kind of objective. We know the objective has some kind of vector. So we kind of slide our line along. And if we slide our line along, while still maintaining feasibility, we have to kind of stay in the range of from here, and we keep going. And where will we stop? We'll stop somewhere. This will be the last point we touch before we leave the feasible region, and we no longer are feasible. So the goal of linear programming, expressed geometrically, is to find that extreme point. Extreme with respect to the direction of optimization. Okay? So if you want to maximize, you go that way. If you want to minimize, you come back this way. If you change your objective, it doesn't change the feasible region. So keeping AX less than equal to be the same and changing the maximization, the C, all that does is say, well, I actually want to optimize this way. No, wait, I want to optimize this way. Or I want to optimize this way. It just picks off some vertex. Okay? Which immediately gives us, so there are a couple of things here. Is it always going to be in one of those vertices? Could it be somewhere, here in the middle? Could it be somewhere inside? Can you say for sure? So you can visually look at this and say, well, it's probably going to be at a vertex. Suppose the line was such that the normal was perpendicular to that edge there. So suppose we had another line that went kind of like this. And stop right here, exactly on this. What's that mean? Oh, there are a bunch of different optimal solutions. That also happens, which includes these two endpoints. So the statement that the optimal solution is achieved at a vertex is not wrong. It's not saying it's unique, that's all. Right? It turns out that even if you go to 3 dimensions, so 3 dimensions, imagine you have some kind of polyhedral structure here, and I have this plane that's going, and it's trying to, it's infinitely big, it's going to go going. It's going to stop somewhere here at this point. It's going to be a vertex there. And this will work with, you can at least visualize or convince yourself what's going to happen. It might again go along an edge, which is fine, but it includes the endpoints, or it might go on a plane, which is fine, but it still includes all the endpoints. You can show in general that for linear programming, the optimal solution is always achieved at an extreme point of the feasibility point. It has to be one of those points. It's not going to be somewhere in the middle, for this reason alone. Now, if you were, for example, optimizing a quadratic function, this may not be true. Suppose you're trying to maximize a concave function. Concave functions kind of look like this. They're big in the middle and they're kind of small on the sides. Right? So think of, say, entropy or something like that. If you put a concave function over this, it's going to optimize somewhere in the middle. Like if you think of a function that's sort of big and then small like this, it'll optimize the middle if you want to maximize. It won't optimize the boundary. This statement I just made will not be true. But for linear optimization, it has to be at one input because you're always going up or down. Okay? So again, I'm not going to prove this here in class. It's an interesting sort of fact that we know. And it's not hard to prove, it takes some work, and I'm going to do it here. So the claim I'm going to make is that every, not sort of, there exists an optimal solution to a linear program at an extreme point of the feasibility. That's some feasibility level. Okay? So I didn't say all optimal solutions because that's not true. I didn't say all extreme points are good. But if you're looking for optimal solutions, it is sufficient to look among the extreme points. One of them is going to give you what you want. Which, by the way, gives us an algorithm for solving linear programming 2 dimensions. What is an algorithm now that you can now come up with to solve linear programming in 2 dimensions? Based on what I just said, based on what we know now. What would you do? So I give you an instance, so give you C, A, and B, it's all 2 dimensions, the 2 variables. I say solve this problem efficiently. Get the optimal solution.
Find all the intersections, check for maximization function, whichever is the maximum return.
So find all the intersections among what?
Among the constraints.
Among the constraints. So every pair of constraints could give you an intersection.
Yeah.
So you write down all possible intersections among pairs of constraints, right? And then you check each one of them. One of them must be an extreme point. So just check the one that gives you the biggest answer. How long will this take? If there are m constraints,
on the
there are m
number
constraints.
of constraints. Yeah.
So the m, so it'll take m squared time. Because you have m choose 2 and it takes constant time to evaluate it.
Yeah.
So in m choose 2 time, m squared time, you can solve linear programming. Which means that if you can take any problem and model it as linear programming in 2 dimensions, we have a solution for that problem. Now, the solutions, it sounds weird, right? Convert this to this weird geometric format and look at the vertices of this polytope again, but it's a solution. And this is what I meant when I said last time that the goal of studying optimization is to put your problem into some general context and now focus on that context itself. Now worry about where it came from. So any problem that I can model as a linear program can now be solved. So you see how powerful this hammer is. If I have a sufficiently rich framework for optimization, I just need one algorithm and I've solved all these problems. Okay. And that works in 2 dimensions. It can also work in 3 dimensions. It can also work in 4 dimensions. But what's the catch?
It's unbounded.
Good. 2 catches. What are the 2 catches here? So catch number 1, the boring one, is that this could be very big. The more interesting catch is the one you brought up, that suppose it's unbounded. Okay, so let's draw this again. Let's try to imagine what the problem is like. Obviously, if my feasible region is closed, everything's great. So something must go wrong, right? So let's draw this again. So let's maybe draw a feasible region that's kind of maybe open. Okay, on one side. Even here, it might be that your objective can be solved. When will that happen? Is if you're trying to say optimize this way, then you'd end up here somewhere. But suppose you're trying to optimize anywhere in the set of directions that goes off to infinity. So suppose your objective C looks something like this, right? And what's going to happen? You can keep going, keep going, keep going. This will never end. Your solution is unbounded. But this kind of makes sense, right? We can actually write this as a simple example. For example, let's say that we already have a very simple example of an unbounded feasible region, where we said x is greater than equals x1 greater than equals 0, and y1 greater than equals 0, right? So let's write this out. So our constraints are x1 greater than equal to 0, x2 greater than equal to 0, and let's say our optimization function is maximize 2x plus 3y. So you can see that the 2, 3 vector is kind of pointing up, and you can do it. Another way to see this without any geometry is to say x and y are positive. I want to maximize this expression. 2 and 3 are positive numbers. I can let x and y get larger. This will get larger. So I can say this algebraically, I can say it geometrically. Again, this back and forth is helpful. So this can happen, in which case you have solutions infinity per unknown. And in fact, you have to be careful sometimes to make sure that when you're framing a problem, you haven't framed it badly so you get unbounded solution. So having a bad feasibility set could lead to no feasible answer, which means you have no solution at all. Having a feasible region that's very weak could mean that the solution is unbounded. All of these things can happen. Okay? And again, hopefully the geometry is what helps you see all this. Okay. Any questions? I was someone was supposed to remind me. You forgot. I also wrote that away. We have like 2 minutes left. I'll put it on Piazza as well. I don't want to bring it up here. There was this point of what I was saying was that it may be that we have to do a sort of in-class exam on Friday and have a take-home component of it as well. The reason is that I would like the final exam to cover everything we've done. That would be hard to do in a 15-minute class without questions that are kind of, you can't ask open-ended questions like assignment questions in a 15-minute thing. I don't think anyone can solve it, homework assignments in 15 minutes. That would be nice, but I don't think it's going to happen. That's not fair. So the kinds of questions I would ask in class would be of a certain kind that you could answer in 15 minutes, and then I would be a larger take-home component to it. Is that something that you're sort of comfortable with? It would say, for example, you would have, 3 to 4 days to do the take-home component of the exam. So I don't want to interfere too much with your other exam schedule, but just something like that. Is that something that sounds reasonable to all of you? Here, I'm not taking a poll. I'm not going to decide this right now, but I just want to get a sense of the room before I post the same thing on the answer for others to talk.
How hard the take-home questions will be the same difficulty as the homework assignments?
They will be so terrible. You will. Why do you ask questions like that? You know what I'm going to say. They will test your knowledge of the material in the class in many ways. Okay. It's like, what? Are you terrorized enough at this point? No, the take-home questions will obviously, yeah. So I think looking at the assignment as a model, but I think even the assignment may be too much of a model because you have 2 weeks or 1.5 weeks for assignment. You only have 3 days for it. So I would say, if anything, it would be maybe less challenging than the assignments, right? But more challenging than what you could do in like 10 minutes. There are certain questions you can ask in 5 minutes and people should know the answer. There are certain questions when you really solve a problem. I'm, for example, one of those people very bad at solving a problem in time-critical manner. I need time. I get stressed. I can't do it. So I'm not going to make you stress to solve hard problems. So that's kind of the sense I would get. Yes?
What would be the submission date for the take-home?
So that's the question, right? So I would imagine it would be the following Monday or Tuesday online. Or it would be, I think a week might be too long, and I also don't want to do a week because you're going to have a whole bunch of other exams hitting you at the same time. So it'd be like, unfortunately, and I apologize for this, it would destroy your weekend, but it would be like Friday the in-class exam, and then Monday sometime the submission take-home exam. This is what I would be. So again, I just want to get a sense of the room here, yeah.
Do we have class Friday for that last week?
That will be yes, there is a class on, wait, is there a class on Friday? I think there is a class on Friday. Are you shaking your head? Is there doubt?
Well, I wasn't sure like Wednesday was the last class, then finals week started like Thursday.
Oh, they have a weird finals week.
I thought the finals week started the next, I thought I checked this, darn it.
It starts on like a Wednesday, it goes to the next Wednesday or something weird like that.
But I thought it's the following Wednesday, because you usually have
Oh, I don't know. I have no idea.
I will, good, thank you, I will check that. If not, then we have to change all the, okay, let me check that one, okay, yeah.
Oh, the 26th, yeah, you should have time, the 26th.
It's a Friday. Okay, so I will check that, but let's look at a translation invariant version of the schedule where I have on day 0 I have the exam, and on day 3 you turn in the take-home version of it. Think about that. I don't want to take more of your time. I think we have the class over, but this is I'm not hearing objections to this plan right now. Is that fair to say? Again, I'm not going to decide this right now, but from the people in the room, I'm not hearing strong objections. Is that accurate? Or hesitation? Or do I hear any hesitation like, I don't know about this? Or not hearing that either? Okay. But feel free to chime in later on Piazza when I post the thing and you can discuss it there. Okay, fair. And I'll check that point. Thank you. Yes. I wanted to give it to you today, and I don't have to give it to you today. Yeah, today for sure. Look for today. It's a random variable with expected values of time today, given the topic of the homework. So.